and welcome to episode number 22 of CS350 Online. I'm your host, as always, Leslie Eisted, and in today's episode, we are actually going to finish the official course content, which I know is 2 episodes before technically the end of the term. But we have other little bonus episodes, I suppose you could call them, to follow. So today we're going to talk about virtual machines. That's our primary thing. These last 3 episodes, just so you know, they're not going to be the full hour and 20 minutes. They're actually going to be a fair bit shorter. So today it'll be talking about virtual machines. And then on Thursday's episode, we're actually going to give you a kind of a really brief introduction to networking, trying to focus on how networking and the operating system are kind of put together, because different aspects of the 5-layer network model belong to different elements of an operating system. For example, things like implementation of TCP/IP tends to be a part of the kernel, and the kernel would provide a high-level API, system calls and stuff, same as you would have print and stuff. So it's really interesting to see how the different layers of a network model will actually interact with the operating system. So that's going to be our next episode. And then the final episode, we're actually going to talk about how do you design your own operating system? What are the design decisions that you have to take into consideration? And we will talk about that with respect to a very specific operating system. And we'll discuss why that operating system might have made those decisions. And it's a really fun operating system for many. So that should be a lot of fun, right? But today's virtual machines. So before we get into virtual machines, just a few things I want to mention is don't forget that assignment 3 is due on April 9th. I think it's April 9th, which is Friday. And the page tables are not required for assignment 3. If you wish to do page tables, however, please go ahead and do that and then submit again on April 14th for bonus marks for doing page tables. If you have already completed page tables, you still need to resubmit for the April 14th deadline. And the reason for that is because when we send the assignment 3 away for grading, it will be grading without page tables, and then the submissions for our April 14th will be sent away for just looking at the page tables. So we need 2 separate submissions, and I know for many of you that's going to be a pain in the butt, but there you go. So for the bonus submission on April 14th, the only thing we're going to be looking at is your page table implementation. So we're going to run a couple tests just to make sure your code actually compiles, and that will be worth a few bonus marks there, because obviously if your code doesn't compile, then you can get some bonus marks for if you've written the code, but yeah. We're not going to give you full bonus marks if your page tables aren't implemented and running. Now, does that mean if you don't implement page tables that you still can get some bonus marks? No, because the bonus marks for the tests actually running are going to depend on the TA's inspection of your code. So if they inspect your code and they see that you didn't implement page tables, then you wouldn't get any bonus marks for the code actually running. So it's kind of, I think you see what I'm trying to say here. So yeah, the bonus is due April 14th at 11:30 p.m., which is our typical time. You cannot use slip days for the bonus submission. Slip days are only for the A3 submission. And you don't have to do it. Like, this is totally optional to do the page tables. Just keep that in mind. The other thing I wanted to mention is don't forget about the quizzes, because we are approaching the very end of the term. And it's really, really important that you get those quizzes done, because if all 200 and change of you are trying to access Learn at the same time, trying to rush those quizzes in the last hour before they're due, that could overload the system, and some of you may not get all the quizzes. And so it's really important that you do that. Now, some of you, I noticed, have been starting to ask questions about what the final assessment's going to look like. And it's going to be in the same form as that you've already seen, which is it's going to be a Learn quiz. And you are going to get more than one attempt at it, and you will see your grade in between each attempt. The reason why we allow multiple attempts is actually because we can't, everybody who's taking this course, we can't assume that you have a functioning computer, and I don't want to assume that you live, in a city with reliable internet. I'm assuming that some of you live in places that have unreliable internet, and you might get booted off Learn, And I want to make sure that it's fair. So you get multiple attempts, and we take your highest scoring attempt. You will not see which questions you get wrong or right. And each attempt is going to be a different assessment. So it is a randomized assessment. So it's going to be longer than the quizzes, so significantly longer than the quizzes. There's more questions. There are different levels of difficulty, so everybody's going to get, N of this level of difficulty, K of this level of difficulty, and so on and so forth, but it is randomized. And it is open book, so you're allowed to have the slides open and anything like that. We will ask you to sign, something that says, I will not cheat. We hope that you don't do that. Obviously, we can't really prevent it, but we will not be using any kind of proctoring software because as we've posted on Piazza, things like, I don't even know what they're called anymore, things like ProctorU and stuff, that's really just a rootkit, and it's really an invasion of your privacy, and I just don't think that's right. So we're going on the honor system here. And we hope that you will go with that. So yeah, your final assessment is just going to be a longer quiz on Learn, and you will know your grade immediately. And you don't have to take multiple attempts. If you're happy with your first attempt, then there's no obligation to do another attempt. The other thing I wanted to say is that if you have questions about the final assessment, it's really important that you make them private on Piazza. Because again, this is a quiz and we want to make sure that, it's fair for everyone. If you do find something that is an error, and that's possible because even in an in-person exam, there's always going to be typos and spelling mistakes, no matter how many times we proofread it. And then if we do notice, we will make the necessary corrections and we will announce it to the whole group. Now, in terms of availability, I think we actually have the assessment available for roughly the whole assessment period. I don't remember the exact dates, but it's not like you can only write it in this 3-hour period. No, we don't have something like that. We've got it open for a while. You can write it, I think it's 2 or 3 times during that period, and we wanted to make it flexible because we don't know what other kinds of obligations that you have on you from other courses. And I know other courses are being a lot more strict in how the final assessment is carried out, but we're a little bit more relaxed. All right, so that's what I wanted to say about that. So let's talk about the OS of the day then. So we have finally gotten to the point where we can talk about Linux or GNU Linux, whichever you prefer to call it. And many of you, okay, I should say all of you have used this at this point. Of course, because if you are actually submitting assignments, then you would have had to actually log into one of the school servers and use the submission system through there. So this operating system came out in 1991, and many of you know that the creator of it is an individual by the name of Linus Torvalds. So this operating system is much, much newer than things like macOS. It's newer than Windows. But there's actually a bit of a story to it. So why did Linus actually go out and create his own operating system? Because that's actually a really good question. Why does anybody go out and actually create an operating system? So the story goes that Linus wanted a fully functional, free operating system. So, I mean, Windows is a fully functional operating system. I mean, I want to say 1991 fully functional in quotes because it wasn't. Probably in terms of what Linus was looking for, I wouldn't say Windows 3.1 or Windows 2 was actually considered fully functional because it didn't support preemptive time sharing, whereas Unix-based operating systems did, and the same is true, of course, for macOS at the time. But also, they weren't free. You actually had to pay for them. You couldn't get the source code and open it up and make your modifications. So the major commercial operating systems obviously weren't meeting his needs. So he looked around to see, what else is out there. So Richard Stallman was working on this thing called the GNU project. But the development of the kernel got stalled. It wasn't released yet. When you're working on free software, you don't have the same sense of urgency towards getting stuff released. Because everybody's kind of implementing this as volunteer work, And you can't force volunteers to do stuff on a deadline. So that's totally understandable. And I mean, if you look at a lot of open source projects, they do get a lot of delays and stuff. Another one that he looked at was 386 BSD, which it was a supposed to be a newer version of the BSD operating system, but it was bogged down with legal complications, so that wasn't going to happen. So he realized that he needed to create his own. So he wanted to, so the idea behind the GNU project, and I don't know how much you know about it, is that it's software that is free. So you don't have to pay anything for it, and you get the source code, and you can do essentially whatever you want to it, so long as you don't take it and then commercialize it yourself. So he tried to incorporate as much of the GNU project as he could, and along with other GPL applications. And if you've ever installed a GNU Linux operating system, like SUSE or Mandrake or Mandriva or Mint or Gentoo or Ubuntu or Kubuntu, you know that Linux isn't just the kernel. There's a whole bunch of other things that come with it, and it's all part of like the GNU project and the GPL. You get all these other different things. So Linus incorporated much of that into the project as he could. The story is that it was originally named Freaks, or I'm not really sure how he would have said that. And then on some blogs, people tried to convince him to name it Linux, kind of after himself. And I don't know how much of that I actually believe, but that's a story for another day, not today. So what is Linux then? I mean, Linux is a Unix-like operating system. It has a monolithic kernel, which is like every other major commercial operating system. So if you look at Mac OS, if you look at Windows, if you look at Android, which is actually a fork of the Linux kernel, they're all monolithic operating systems. They all put everything into the kernel. Now, Linux actually isn't as bad at this as some of the others. So if you're looking at things like macOS and Windows, a lot more stuff is in their kernel than I want to say with Linux. Linux actually has stuff separated out a little bit better in my opinion. Keep in mind, most of my development I actually do under a Linux-based environment. But what you will find in the Linux kernel is things like memory management, so virtual memory, interprocess communication, that's IPC, scheduling, file systems, device drivers, all of that is incorporated into the kernel. Now, device drivers is kind of funny. Sorry, I'm trying to find my mouse, and when you've got a giant screen beside you, it's actually kind of hard to find. Normally... Because when I have these giant screens, I actually usually use this little app called X-Eyes, and it's two little eyes that sit in the center of your screen, and the pupils actually point to where your mouse is. But I don't know if that exists for Mac, but I don't think it matters because I'm pretty sure that I'm going to run a different OS starting next term. All right, so device drivers is kind of funny with Linux because some device drivers actually don't live in the kernel. So a lot of printer drivers are actually not in the kernel. They're actually user programs. So I can actually safely say that a lot of things like so a lot of Epson's printers for dot matrix printers, a lot of their printer drivers for things like their POS devices actually are not kernel modules. They're actually just user programs, which is kind of cool. They're like plugins to Ghost Script. So that's kind of neat. So Linux is kind of funny in that some device drivers actually don't live in kernel land. Some of them live in user land. Some other interesting things is that the windowing environment is actually not a part of the kernel. And things like Qt and all of that, those things are not a part of the actual kernel. Other interesting things. So because Linux is this free open source project, anybody can take the code and do whatever they want with it. Like if you want to take the Linux kernel and modify it so that it runs on a Raspberry Pi, like as an embedded OS, you can do that. And people have done things like that. That is your prerogative to take the kernel and do what you want with it. If you want to take the kernel and you don't like the scheduler that Linux uses, which is the completely fair scheduler that we talked about in the scheduling section, then change it out. if you want to take the Linux kernel and you've decided that you only want to support x86 architectures, you don't want to have any support for PowerPC, and you don't want to have any support for RISC-based processors, you can strip all of that out. That's your choice. You're allowed to do that. And as a result, there are so many different variations. Now, most of them actually still live on the base Linux kernel, but there's just so many different distributions of it at this point. And what's also interesting is Android is actually based off of Linux. It's a fork. So I kind of wanted to show you this cool picture that admittedly I got off Wikipedia, but it's really, really neat at showing you kind of the layers and the complexity that you have here. So in black, what you've got is the actual physical hardware, the bare metal of the system. So things like the CPU, the GPU, different sensors, your actual Ethernet, physical ports, and things like that. And then in red, and I apologize to anyone who's actually colorblind here, but sitting right above the hardware, you've actually got the Linux kernel. So these are things that would run in the protected mode. And so that's going to be things like your device drivers for your graphics cards. That's going to be like your sound driver. So you can see here you've got ALSA. You've got your network components. This is going to be your file systems, and all of that is all going to live down here in the Linux kernel. And over here, this little smaller red square, this is the Android fork of the Linux kernel. So it's kind of very similar. And then sitting on top of that in a more user land, you actually have kind of the base libraries that everything else is built on. So ones that you'll be familiar with are glibc and the X server. And they say X server, and something that's really confusing, I think, to a lot of people is how many different versions of X there actually are. So, I mean, I started by using X11R5 and X11R6, which is one of the different X servers that you can have. But a lot of people these days actually use X386, so there's other versions. Some of their window managers also live down here, and you've got other basic libraries like audio libraries, and so on and so forth. So those are kind of like your base libraries that everything else is built upon. And then on top of that, you've got things like GTK, GTK++, Cairo, which is like a graphics library, Qt. So GTK is for GNOME-based applications, and Qt is kind of where KDE went, though that separation isn't as big anymore as it used to be. And then you've got things like FLTK and WX widgets, the Unity desktop environment, which is used by Ubuntu. And then on top of that, so you've got other shells. And then on top of that, you've got the actual user applications like the user would actually create using these different layers of libraries. So things like games and VLC and TuxRacer, and so on and so forth. Actually, true story. So, I don't know how many of you are big fans or like home users of GNU Linux-based operating systems, but one of like the classic games that used to exist on Linux, so it was this game known as TuxRacer. I'll try to bring a little picture here. So the reason why I bring up TuxRacer is it's actually connected to Waterloo. So TuxRacer, again, I'm just trying to bring up the picture. Let's bring some images here. Fun story about TuxRacer. So here's TuxRacer. You're a penguin and you get to race down mountains and stuff like that. It's kind of a fun, silly little game. So why am I mentioning TuxRacer? So this was one of the GPL games that you could actually, it usually came packaged with KDE and stuff. Why is this cool? So TuxRacer was actually a final project in CS488 many, many years ago. So there's a little Waterloo connection for you. So yeah, that was the 488. And for those of you not familiar with 488 is, that's our graphics course. And the graphics course, the final assignment is for you to do a project of your choosing. So some people choose to make a game, which generally isn't recommended because game development involves a lot more than you realize. But yeah, so This the person who actually created it, their name is Jasmine Patry, and she created TextRacer for her 488 final project. So that's kind of a cool thing. I think it's cool anyways. All right, so one other thing I just wanted to show for those of you who are not that familiar with using Linux is the fact that one of the things that I really like is how much freedom you get out of the OS. Like, it's really good for development, but the other really cool thing is the fact that you get, if you want to use a different windowing library kit, if you want to use a different desktop environment, you can do whatever you want. So there are so many different ones. So this is Enlightenment, which a good friend of mine used for a number of years. It's not, to me, Enlightenment looks kind of like Mac OS combined with TWM, which is the window manager, which is what we used to use. And then here's an old version of KDE, and there's just so many. And I mean, if you log into any of the school machines with the desktop environment, you're going to get Unity. There are so many different ones, and that's one of the big things you get out of a free open source OS is freedom to do whatever you want. I like that. I like that a lot. It doesn't always work out in your favor, because sometimes I find the when you don't have a company backing things, sometimes things are a little bit buggier, but that's the beauty of it. Since it's open source, you can go in and fix the bugs yourself. Anyways, that's a rant. All right, so we're not going to do a recap. We're just going to kind of jump in to our topic of the day, which is looking at virtual machines. So this is actually a pretty short little module here. Why virtual machines are interesting to talk about is, well, they kind of review all of the topics that we've covered throughout the whole course. And virtual machines, whether you realize it or not, are something that you've actually been using since the beginning of the course and quite possibly before. So what even is a virtual machine? Well, a virtual machine is a fake computer. It's, you have some computer and you've either simulated it or emulated it. So for example, our operating system OS 161 is built for a MIPS R3000. Now, I'm going to take a wild guess and say that none of you actually have a MIPS R3000 platform that you could do development for. Now, admittedly, some of you probably have PlayStation 1s and PlayStation 2s at home, but probably not in a state that you could actively develop on them. I don't know. The only PlayStation that I actually installed the general purpose operating system on, it was my PS3. I installed Linux on it, and I think I actually used that as my computer for an entire term at school because all of my actual computing hardware broke. Let me just say that the PS3 does not really have enough memory to do it. It kind of sucked. So, in order for us to run OS 161, we use a tool called Sys161. Sys161 is an emulated or simulated MIPS R3000. It's fake, it's not real. But we use that program to run OS 161. And that is, in a way, a virtual machine. It's a very primitive kind of virtual machine, but it is still a virtual machine. What they give us the ability to do is we let a computer act as other computers. So we can have one computer be standing in the place of many other different kinds of computers. And what's interesting is that when you have these virtual machines, you can run operating systems on these virtual machines. And you've seen this through OS 161 running on Sys161. So you are running either Mac OS or a Linux-based operating system or Windows, and you are running within that OS 161. So these virtual machines let us run operating systems within them, and that actually gives us a lot of interesting abilities. Now, there's generally a rule when we're creating virtual machines. The operating system or whatever programs you are running on the virtual machine should not be aware that they're running on fake hardware. They should never know. I shouldn't have to modify my operating system or my user program such that it can run on the fake hardware. I should be able to take an off-the-shelf copy of Windows 95 and install it onto my virtual machine without making any changes. Now, obviously, with OS 161 and Sys 161, that's not possible because ours is very simple. And in truth, a lot of virtual machines do require special patches to make things run properly. But that's a story for later. But ideally, a virtual machine should be implemented in such a way that the operating system, the guest operating system we call it, is not aware that they're not running on real hardware. Now, here's a really interesting thing. So this concept of virtual machines, it probably seems like a really modern idea, but it's not. So the idea of a virtualization actually goes back to the 1960s, so really far back. But the reason why you didn't see that be popular in the 1960s, the 70s, the 80s, or the 90s was that performance was really, really bad. And we're going to talk about why the performance was bad. And it wasn't until 2005 where we actually start to see VMs being possible again. And I actually remember this because I used to dual boot everything. And then after about 2005, and I think for me it was about 2007, I actually started using virtualization so I didn't have to dual boot. Because it's a pain. Like, if you're in one operating system and you need a program that's only available in the other one, but you kind of I don't want to have to reboot my computer to go use MATLAB and then have to reboot to go back to what I was doing. I don't want to have to reboot to go play with Photoshop and then come back. So virtualization led to me not having to do that. I could have both OSs running at the same time and I wouldn't have to reboot. So why was the performance a problem? Well, it comes down to the two different ways that we can implement these. And we'll get to that in just a minute. So just before we get into how the virtualization is actually implemented, let's just review some of the things that exist in our systems. So we know that our computer is comprised of a bunch of actual physical devices. You've got a CPU, so maybe you've got an Intel i9 or an i7 from the old Nehalem generation. Or maybe you're looking at these brand new AMD Ryzen 5900 HXs, which I'm looking to acquire right now. Or maybe you've got a CPU, some CPU, and then you've got some amounts of RAM, hopefully a lot, because that's really good. And then you've got a bunch of other devices that make up your computer. You've got, a graphics card, and maybe you've got 2 or 3 of them, and you've got network cards, and maybe you're getting these lovely little SSDs that are not plugged in by the eSATA, but plugged directly into the PCIe buses. There's all kinds of physical hardware that you have in the computer that makes it as a whole. And you know that the CPU is going to execute all of the instructions, both of the operating system and the user programs. And we also know now that in order to separate the kernel, abstract it away from the user program, we actually use a CPU privilege mode to keep them separate. And while OS 161, we only used 2 privilege modes, unprivileged for user and privileged for kernel, in reality, modern processors actually have about 4 levels of privilege. And if you're running your operating system on the bare metal, you're only probably using 2 of them, but we're going to start using more of them shortly. It's exciting, right? So the operating system environment, we know, actually does most of the actual heavy lifting for creating the execution environment for the program, which means, finding an address space and managing the virtual memory for it, keeping track of open files, keeping track of threads, handling things like the scheduling of the threads and the priorities of the threads. We know that the operating system does all of that to create the execution environment for the user program. It loads the user program and it tells the user program, okay, go. We also know that the kernel is going to be responsible for handling all of the interrupts and exceptions raised by the CPU. So interrupts, remember, are things that are happening from the hardware. So you push a key on your keyboard, that's a physical hardware interrupt. You divide by 0, That's a software exception. You try to write to read-only memory, that's a software exception. That's something the code did that was bad, not the hardware. And we know that the kernel handles all of these things. It also manages memory and implements concurrency. Okay? Keep this in your mind when you're thinking about how am I going to support this on a fake piece of hardware. So let's talk about our first attempt at implementing a virtual machine. So the first attempt is that our virtual machine itself is simply a translator. This is kind of what sys161 is, by the way. So what it's going to do, so we have what's known as the bare metal. So by the way, this would be like one of my own computers. So you've got your bare metal, your Intel i9 CPU, or maybe you got an i7 or an i5 or an i3, whatever, or Ryzen. And then your host operating system, maybe it's Linux. Your virtual machine is the guest hardware. And what it is in this very basic example, our first attempt, is it simply translates. So it's going to take instructions from the guest operating system and the guest user programs that are running assembly and MIPS, and sys161 is simply going to translate the MIPS instructions to x86 instructions. And then it itself, so the sys161 virtual machine, is just a user program that is running on the host operating system. So we are translating our guest operating system and user programs through our guest virtual machine into the host's language. But this raises a lot of really interesting discussions. So this translation process is actually fairly straightforward, as you can imagine, because we already know how to write compilers and assemblers. So we simply are going to take every instruction and we are going to capture each call, and we are going to translate that from one assembly language into the other. And there is a lot of details that have to happen, because if you look at the MIPS architecture or RISC architecture, it's a reduced instruction set, and you generally have more general purpose registers than the CISC architecture of an i9, which has an insane instruction set and very few general purpose registers. But that's what we're doing, is we're capturing the instructions and translating them for the host operating system. So then we have some interesting questions. So what happens with interrupts or privilege and virtual memory? So for example, in our guest operating system, so you might recall that when we acquire a spin lock, we disable interrupts. Whose interrupts are you disabling exactly? Are we disabling sys161's interrupts? Or are we going to go all the way down the chain and try to disable our bare metal interrupts? Obviously, I do not want to have a user program try to disable my bare metal interrupts. That would be very bad. So we have to be able to capture those things and figure out appropriate behavior. And usually what this means is that as part of the instruction capturing process of our VM in this very simple approach, is we're going to have to say, okay, we see that you're trying to do this task. We are either going to emulate that behavior here, or we are going to make appropriate system calls down to the bare metal. So for example, if I wanted to write to disk, I might have to capture that instruction here and then translate that not to an assembly instruction, but to the actual system call assembly instruction. So we have to be very smart about this. This is kind of slow, okay? This is not fast. You're never going to have this be fast. So some of the big problems when we're thinking about how do you actually implement virtual machines is you have to ask yourself, so what do we do with interrupts then? So for our simple example here, we said, okay, we'll just capture it and fire appropriate system calls. But we still have this fundamental question. If I'm disabling interrupts on the R3000 because I just acquired a spin lock, should I really be trying to disable interrupts on my bare metal as well? Like, does that really make sense? So it's actually a pretty big question. How do you handle interrupts? Disabling and enabling them. How do you handle hardware interrupts? Are you going to forward them, pass them down? It's a big question. If I push a letter on my keyboard, which operating system receives that interrupt? Does Linux receive that? The host OS receive the interrupt? Or does the guest OS receive that interrupt? There are lots of big questions about how do you handle interrupts with a virtual machine. Other things you have to take into consideration are how is virtual memory handled? One of the interesting problems that can arise is if both the host and guest are using paging, depending on how you implement, you can actually end up with collisions in physical memory, and that can be a pretty big problem. Now, for our the naive system we did here, this actually isn't an issue because our guest operating system is running as a user program, so it's even though our guest OS may have its own implementation of virtual memory, it's not quite real, and the physical addresses it's using are actually just user addresses. So there's no issues there. But there are other ways that you can implement virtual machines that can be a problem, and we'll talk about that. I always scroll the wrong way. So let's now talk about the different kinds of virtual machines. So first off, that was a really naive approach we took. And what we really want to talk about is something called a hypervisor. A hypervisor is a virtual machine manager. And there's two types of hypervisors that exist. There's type 1, which has a hypervisor running on bare hardware. And then there's type 2, which you're probably familiar with. It's a hypervisor that runs on the host OS. So if you look at the difference, so the type 1 hypervisor, you have the CPU, and then the type 1 hypervisor runs on the bare metal, kind of like its own operating system. And then all of the virtual machines run on that type 1 hypervisor. This is probably not something you're used to using. This is not something that a consumer would typically have direct access to. What most home users have is a type 2 hypervisor, things like VirtualBox, things like Docker, and things like VMware. A type 2 hypervisor, so you've got your bare metal with your host OS, and then your type 2 hypervisor, so VMware, VirtualBox, what have you, and then the VMs run on that type 2 hypervisor. So our type 2 hypervisors are running as guest programs on the host operating system. So the big difference between type 1 and type 2, of course, type 1 is running on the bare metal. That means they're running in privileged mode, and the VMs themselves will run in less privileged modes. Now, you noticed I haven't said unprivileged modes. I said less privileged modes. To solve some of the issues with type 1 hypervisors, we're actually going to make use of the fact that CPUs have a variety of different privilege levels, not just 2. So unprivileged instructions will execute completely normally. So any unprivileged code that is running in the type 1 hypervisor, so let's say your user programs on your VM, is just going to run normally because it's unprivileged and it didn't need any privilege. But where it gets really interesting is when privileged code, like the guest operating system running on the VM, what happens to privileged instructions. So they're going to have to trap to the hypervisor, and the hypervisor will handle how that behavior happens. So the hypervisor might pass these through for instruction. It might emulate or simulate the behavior of others. So how things get handled really depend on what kind of instruction you have. Type 2 hypervisors, on the other hand, run completely in an unprivileged mode. And any unprivileged instructions, as I mentioned with our naive implementation, are going to be just translated and executed like a regular user process. But then for privileged instruction system, what we're going to do is catch them and either simulate their behavior or have the type 2 hypervisor make a system call on the behalf of the guest. Again, and that's going to make it really, really slow. So if you've ever wondered, why is stuff slow running through VMware or VirtualBox or Docker? It's because it has to do these translations and then simulate or create system calls for any privileged instructions. And it's really not fast. It's getting better. I do have to admit, it is getting a lot better. It used to be really bad, though. Okay, so let's talk about this concept of privilege. So we're kind of not going to talk a lot about the type 2 hypervisors because I feel like they're actually fairly straightforward. They don't suffer a lot of the same issues that type 1 hypervisors solve because the hypervisor is simply going to be the translator, and it's going to either emulate or make system calls on behalf of the guest. So that it's actually fairly straightforward. We don't end up with these virtual memory problems that we would with the type 1. So we're going to kind of focus more on the type 1s because they're kind of interesting. So how do we handle privilege? So operating systems and user programs can both make privileged calls, but only an operating system should be allowed to do that. The user program would make a privileged call maliciously or in error. And we have to make sure that if a user program is running, we are running in an unprivileged mode, and I have to make sure that we throw an appropriate exception to prevent the user program from actually executing that privileged call. And if you are running on a type 1 hypervisor, how do you differentiate? Because the VMs are running in an unprivileged state. How do you differentiate between the operating system, the guest OS, making a privileged call and the user program making a privileged call? If you only have 2 privileged modes, you can't differentiate this, which is why we use rings of privilege. And this is why I said a different level of privilege. So modern hardware usually supports a minimum of 4 different privilege levels. Now, if you're running your OS on bare metal, you usually only use 2, which is privileged for kernel and unprivileged for user program. But if you are running a type 1 hypervisor and a VM, and then a guest OS on that, we're going to make use of these rings. So the VM will run, so the type 1 hypervisor will run in the highest privileged mode. And then the VM can run in the next lower privileged mode. So it's not unprivileged, but it's low. It's not as much privilege as the type 1 hypervisor, which means that the operating system will run in a kind of mid privileged mode, and then the user program truly runs in an unprivileged mode. And that will let us differentiate between the kernel doing something bad, making a privileged call, and the user maliciously making a privileged call. And so that is how we can actually differentiate and have the hypervisor handle this appropriately, or the VM handle it appropriately. And something to think about then is, how does the type 2 hypervisor differentiate then between the OS, the guest OS, and the guest user programs making privileged calls? It's an interesting thing. Well, we have a simulated CPU, so we can have a simulated privilege. So there's some pretty easy ways to actually handle that. All right. Now, how do you handle virtual memory with a type 1 hypervisor? Again, with the type 2, it's pretty simple because everything's running as a user program. There's not that, it's code you have to write, but it's not that complicated. With the type 1 hypervisor, we end up having some interesting problems. So how are we going to have a bunch of operating systems share the physical memory? One strategy that you could do that's fairly straightforward is you could simply take your physical RAM and you could divide it into a bunch of chunks and say, okay, this chunk is for this VM, this chunk is for this VM, this chunk is for this VM. And we can do some remapping in Hypervisor to just say, okay, you get this, you get this, you get this, and okay, we'll remap it. So instead of each of you getting the full 32 gigs, each of you now gets 8 gigs. So we can run 4 of you. But that's the problem with that, is when we subdivide the RAM saying, you get 4 and you get 4, what if some of them don't use all 4? And what if some of them need more? And what if you want to run more VMs? So it's very restrictive. But if we don't restrict it, if we let each each of the guest operating systems actually use the full RAM, then we're going to end up with collisions where one OS is using one part of physical memory and the other OS thinks it's using the same part of physical memory. That's a problem. And so, I mean, this idea is good because we want each of the guest operating systems to think they have access to the full 32 gigs. But the problem comes with the collisions in the page tables because the OSs wouldn't know about each other. That's a big thing. You don't want the OSs to know about each other. So how would they manage not overlapping in physical memory? Well, this is where the Type 1 hypervisor has to play a role in actually giving the pages to the different guest operating systems. So what they do here is the Type 1 hypervisor creates a shadow page table. And every time the operating system wants a frame of physical memory, they're asking the Type 1 hypervisor, although they don't realize it, to give it a frame of memory. And the Type 1 hypervisor, it's mapping the physical frames into its own page table, and it's keeping track of which guest operating system is using which pages, so it can actually give a frame, and it's giving it only to that guest OS. So we're adding another layer to the page tables. It's the shadow thing. Now what's really interesting then is, so how do address translations work? Are we going to have every translation have to go through the hypervisor? We don't want that. We already know why that's bad. We know that's bad because that's involving your operating system in every single address translation. That's not a good idea. So what we want really is we want the shadow page table to actually be supported by the MMU. And indeed, extended page tables have been supported in all modern operating systems from the Intel Nehalem architecture onwards. So Nehalem, for those of you who are not familiar with that term, was the first generation i7s from Intel. And they were released, like, I want to say it was 2007, except I know it wasn't the summer because I was working at Google and we had to sign up, and we had a bunch of NDAs we had to sign because we were working with the architecture before it was released. So I want to say maybe it was late 2007 Nehalem was released, or maybe early 2008. So we have had support for extended page tables for Type 1 hypervisors since about late 2007, 2008. So that's pretty cool. Also, one of the reasons why virtualization hasn't been really popular since about 2005 is because in order to make all of this work for Type 1 hypervisors, we actually needed physical hardware support. We needed more levels of privilege. We needed the MMU to actually understand extended page tables, or the shadow page table. So now what happens is all of the actual address translations can go through right to the MMU, and if we need to do so if we have a page fault, it'll go then to the Type 1 hypervisor. And but that'll only be if it's on the shadow table. Otherwise, the Type 1 hypervisor would forward it to the appropriate guest OS. It's kind of cool, right? How then do we handle I/O and devices? So if you are a guest operating system and you want to write to a file, or write to disk, or read from disk, this is fairly straightforward. In a Type 1 in a Type 2 hypervisor, you would be making system calls. That's all. Your Type 2 hypervisor would just translate those to system calls for the host operating system. In a Type 1 hypervisor, we have a lot of options. There's a lot of different things. So one of the questions that is, is the file system actually presented to the VM? That's an interesting question. So one of the things that you can do is you can give each VM its own physical partition, and then each VM can actually manage the files itself. Another way that files are typically handled or file systems are handled with VMs, especially Type 2 hypervisors, is, have you ever wondered how you get like a disk in VMware? It creates a file. Your file system, your disk for your VM is just a file itself on your host file system. So that's kind of a neat way of doing it. And whenever you write to disk, you are making a system call to write to that file. So that's kind of neat. I think it's kind of neat. Now, what about input-output devices of other kinds? So keyboards and mouse input. So one of the things that you can do is you can let devices be assigned to a specific VM. So the keyboard is now currently assigned to this VM, and that lets all devices that all interrupts from that device will pass directly through to that VM. You have to consider so that's one easy way of doing it. Another interesting problem we have is device isolation. So let's say you've got a whole bunch of VMs running, and a bunch of them are sleeping, and one of them is active. An interrupt from a device should not go to all the sleeping VMs. It should only go to the one active one. So we have to make sure that interrupts are not interrupting every VM, that we have to make sure we're isolating devices to particular VMs. And generally what we're doing is interrupt redirection. So interrupts from a particular device are going to be redirected towards a simulated interrupt on a specific VM, and your hypervisor is going to handle that. And I know one thing you might notice is, like if you're using a Type 2 hypervisor, if your mouse is over the VM window and you click in it, that's going to pass the mouse events into the guest operating system. And then if you move your mouse towards the edge, the Type 2 hypervisor will be like, oh, you must be trying to access the guest or the host operating system. So now we will stop passing those mouse events in, and we'll let it go to just the host OS. So there's a lot of really interesting things, but in order to make this work, you actually need hardware support. And again, this hardware support wasn't really available until about 2005. That's a really rough overview of how VMs work. And I mean, this is a huge area of research right now. But why are we using virtual machines? I mean, for me, one of the reasons why I use virtual machines, and I've used virtual machines in the past, is because a lot of the time I'm doing a project which requires development on one platform, but I might need to use some tools that only exist on another platform. So for example, sometimes I like to do my development in a Unix-based operating system. I just find GCC is a lot nicer to use. And so I will have like a VM with my GCC development. But if I'm using like Vicon Blade, which is a motion capture tool, at the time, I only had the drivers for Windows. So I would try to generate some data in Windows and use it in Linux. I didn't want to reboot my computer. So I started using a VM so I could have both open at the same time. But where a lot of people really use VMs is actually to create a sandbox environment for users and programmers. So yes, you can create a sandbox. Maybe you want to test development of an Android or an iOS app. Then you'd use a VM and run that OS, and then you can test your program on it, right? Because sometimes you don't physically have that hardware in front of you, or it's a pain to transfer your demo program from that. What if there's a bug? It's a lot easier to do your sandboxing, your testing on a virtual machine than in the actual physical hardware, especially if you don't have it. Another reason why people actually use VMs is maybe you didn't want to pay for a particular piece of software, so you went on BitTorrent and you downloaded it, and then you have to ask yourself the question, is this infected with a virus? Well, the safest way to run the program is to run it inside a VM, because the virus shouldn't be able to escape, because they are isolated from each other. The guest and host operating system are sufficiently isolated that if you have something that you are very suspicious of, running it in a VM will protect your host. So that's another reason why people do it. Another one is resource utilization. And this is actually kind of an interesting story with Amazon. So Amazon didn't always have Amazon Web Services, so AWS. That's not always existed. My understanding of how that actually came to be is Amazon had to, in order to support holiday traffic, like around Christmas time, they actually had to add a lot of computing hardware to deal with that. And the problem is in the down season, so in the middle of the summer, a lot of that hardware was sitting idle, which means they're losing money on it. So they had this idea of what if we could rent time out on those machines and get recoup some of those costs. So it's kind of, my understanding is that's kind of how Amazon AWS gets started. And then that kind of took off because people now didn't have to invest in all this computing architecture themselves and the maintenance of it. They can just pay Amazon to rent time on their own hardware. And so now Amazon actually builds data centers specifically for this purpose. And if you actually look at Amazon, you can actually see that they're using VMs extensively in what they're offering. So this is the Amazon EC2 Elastic Compute Cloud instance types. So they actually have some bare metal offerings. So they have actual physical Mac hardware and they have actual Android hardware. And you pay per hour. So per instance per hour, there's a price that you'll actually pay for that. But what most people use is, if you look at these other ones, these are virtualized systems. So you are getting, see, they say vCPUs. So there's the Nano, which is 2 virtual CPUs, and then all the way up to extra large, which is 8 virtual CPUs. So you can create a virtual machine on Amazon to your specifications, and you can even choose what OS it runs. Obviously, they don't have every combination in bare metal, so they're offering virtualization to give you whatever you need, and then you pay per the hour. So it's actually a pretty cool system, and this is all possible via virtualization. So that's really neat, I think. And of course, now you've got Microsoft offers this, and you've got Google offering it, and there's like, is it Rackspace? I don't know. A whole bunch of people offer different cloud services. We're creating a VM in their data center that becomes your compute hardware to use. And I've actually used AWS a fair bit because I have some computing power at home, but do I want to abuse my own hardware doing a crazy ray trace, or do I want to rent some time on somebody else's machine and just not worry about what happens? I'd rather rent time on somebody else's machine. And by the way, if you ever want to use something like AWS, I think you get there's a free tier that's like 750 hours a month or something for free. So if you ever need some extra computing time to do a little test or something, it's something it's actually worthwhile looking into, I think. All right, so that is kind of our brief overview of virtual machines, which kind of reviews all of the different topics we've covered through this course. So that is the end of all official material for the course. The next 2 episodes, again, they are going to be networking and the operating system, and then how to design an OS. Those 2 are not covered on the final assessment. They're just being offered for fun. And for anyone who's interested, so you don't have to tune in, but you can if you want. Other than that, we hope so far you've enjoyed all of the official material. And we'll see you on Thursday for some fun topics.